introduction, and thank you for the invitation to speak at this wonderful conference. My talk today will be about the singularities that appear in the context of the minimal model program. And as you know, the seminal paper of Birker, Kashini, Hakon, and McKernan established this large part of this program in any dimension over the complex numbers. Recently, a lot of progress has also been made towards establishing this program in positive characteristic and even over base ring of mixed characteristic. And in this general context, this program has been established up to dimension 3, and this was the topic of Joe Waldron's lecture yesterday. As you know, in the context of the minimal model program, one has to introduce singularities. If you start with something regular or something smooth, after some steps, singularities will have appeared. The definition of the class of these singularities does not depend on the characteristic that you are working over. However, as we will discuss today, the homological properties that these singularities have highly depend on that characteristic. So I will start my talk today by giving some examples of the singularities that I will be discussing. And I'm also going to quickly recall the general definition of the singularities over an arbitrary field. I will also discuss the homological properties, so the homological depth properties that these singularities have. And here we would see that these singularities behave very differently if we are over the complex numbers or if we are in positive characteristic. So this is the first part, so it's going to be introduction to non-canonical and KT singularities over a field. And in the second part of my talk, I will discuss how this pathological behavior that log-canonical singularities have in characteristic P plays a role when trying to formulate a proper moduli theory of varieties of general type in positive characteristic. So the second part of my talk will be on the moduli theory of varieties of general type. So these 2 points will take up the majority of my talk, and I will end today by focusing my attention to dimension 3. And this will also be the occasion when we can state some positive results, and we will see how these results on threefold log-canonical singularities can be applied to the moduli theory of stable surfaces in characteristics P greater than 5. So this will be dimension 3. And here I'm going to state the main result, and this is joint with Fabio Barnasconi and Schott Patek Fabi. Okay. So we're going to start with a very well-known and simple example. Let's say we have an A1 bundle over a smooth surface defined by some ample line bundle L. And suppose that we are contracting a section, then because this is a threefold, we could either contract it all the way down to a point, or we can contract it to a curve. So in both of these cases, the resulting threefold is singular, and there is a very clear geometric quotation to tell us if this is a KLT or log-canonical singularity. Okay, so let's assume that the picker rank is 1 here, then this cone is KLT precisely if the anti-canonical divisor here is ample, so we have a cone over the Pezzo surface, and it's log-canonical if and only if minus kx is nef. So this is a strictly log-canonical singularity if this is cone over Calabi-Yau. Okay, so in this situation, it's very similar. So suppose that the surface x is contracted onto the curve C via a fibration that has also relative picker rank 1. then similarly, now this, so this is vibration F. Now this relative cone is similarly KLT if and only if the anticanonical is F ample, so it's ample over the curve. And similarly, this is log canonical. This is F-MEF. So in particular, we will come back to this. If this is a minimal elliptic surface vibration, then this is a strictly log canonical singularity. Okay. So let me just quickly recall the general definition of the singularities over any field. And then we will start discussing what happens for the singularities, well, the properties of the singularities. Okay. So if X is normal and projective, and we assume that Kx plus some divisor is Q-Cartier, where this divisor is effective with coefficients less than or equal to 1, then if we have any birational morphism from Y, where Y is also normal, then something is contracted, and we can suppose that this exceptional divisor has some n components like this. Okay, and so now if we pull back the canonical divisor from X, so we assume that this was Q-Cartier, so this makes sense. And this will be outside of this exceptional divisor, the same as the canonical on Y, plus a birational transform, and then we will have something that is supported on this exceptional divisor. Okay, and so these are some coefficients that make this equality true. So maybe then for the exceptional divisor, there exists such that this equality holds. Now, the definition of these singularities is in terms of these coefficients. Okay, let me write it here. So we're going to say that this pair is KLT if for all such birational morphisms F from all such normal varieties Y, all of these coefficients are strictly less than 1, and we also want these coefficients of this boundary to be strictly less than 1. Similarly, this is log canonical if for all such birational morphisms, now these coefficients are less than or equal to 1. Okay, so this makes sense over any field. So now let's, no, sorry, I want to have one more terminology. I also want to introduce terminology that if this coefficient is equal to 1, then we say that this EI is a log canonical place of this pair, and the image is a log canonical center. Okay, so let's just see an example of this. So if we are in the situation of a minimal elliptic surface, so Kx is F-trivial, then this curve C here is a minimal log canonical center. Because this is a log canonical place, it's not hard to see that the coefficient is 1 precisely because we have this. And so the image is a log canonical center, and moreover, it's a minimal log canonical center. And so I just wanted to point out that for any closed point in here, this is not a log canonical center. So this will come up later. So any closed point inside here is not a log canonical center. Yeah, so I started with a smooth one. Here. Yeah, I started with a smooth surface. It's a very easy example. Okay, so let's try to start discussing what homological properties these singularities have. Okay, so far we were over any field, and now we will have to distinguish if we are over the complex numbers or over an algebraic closed field of positive characteristic. So let's start with what's happening over the complex numbers. So over the complex numbers, KLT singularities are always Cohen-Macaulay. And they are also rational singularities, but I will be focusing on this being Cohen-Macaulay. So the cohomological depth at any point is the best possible. It's equal to the codimension of the point. And very importantly, this implication here, it uses some vanishing theorems. So this uses Kodaira, or more generally, the Kawamata Vivek vanishing theorems. So it has long been known that these vanishing theorems in general fail in positive characteristic. So in characteristic P, these theorems fail in general. And moreover, this implication can also fail from dimension 3. Okay, so let's just briefly recall how this looks in this setting. Okay, so say here we have a point of codimension 3. And we are interested in knowing if we are Cohen-Macaulay or equivalently S3 at this point. Okay, so we can compute this local cohomology because it's just the cohomology of this line bundle on this smooth surface in all possible integer powers. And now, if X is Fano over the complex numbers, then this is 0. And this is implied by the Kodaira vanishing. So we see directly that in this example, this is a direct consequence of the Kodaira vanishing theorem. And similarly, these examples here of KLT singularities that are not Cohen-Macaulay, they are constructed as follows. There are Fano varieties of pick rank 1, such that you have a failure of this Kodaira vanishing for some ample line bundle. Then you take the cone over them, and you get KLT singularities that are not Cohen-Macaulay. So this is how these examples. So my focus of my talk will be on log canonical singularities. And log canonical singularities are, of course, not Cohen-Macaulay, because if you take the cone over an abelian surface, then you are not going to get all of these homologies being 0, and so you are not S3 at that point. So even more general, log canonical singularities are not in general S3, right? But there is some subtle property that they do satisfy. So let me... So our main object of discussion today will be the following theorem over the complex numbers. I'm going to call it theorem star because we will revisit it repeatedly. And it's due in some form to Ambro and Fungino, and the most general form of this theorem is due to Polar, and that form is more general than the one I'm going to state here. So the one I'm going to state here is that if x is log canonical, then, as we already said, x is not S3. But if we look at a point in x that is not the generic point of a log canonical center, then we are actually S3 at that point. So an x in x, so I write not a log canonical center, but of course I mean the generic point of a log canonical center. Then the depth is greater than or equal to the minimum of 3 and the codimension of the point. Okay, so I want to unravel what this says. So let's just look at this example one last time. Okay, so we saw here that for any closed point inside of this relative vertex, this is a point which is not the log canonical center. So this theorem tells us that over the complex numbers, this homology group should be 0. So I just wanted to say a couple of words on how you can see this in this example. So this second local homology group, you can try to compute it, and you can do it by taking this resolution. Okay? And then if you consider the linearized search spectral sequence, then actually you can compute that this local homology is equal to the sections supported at this point x of a sheaf on this curve C, and that sheaf is the higher direct image of the structured sheaf of the fibration that you started with. So this is of the surface, x over C. And actually, in this example, this computation works in any characteristic. Sorry, in all characteristic, yeah. And now, maybe I can write this here. Over the complex numbers, this group is 0. So if you want, so if this was given by a minimal elliptic surface and this curve is smooth, then you can decompose this into a torsion part and a free part, and that torsion part is going to be trivial over the complex numbers. But this actually is a special case of a sort of subtle vanishing theorem that we have over the complex numbers. So a different one. And this vanishing is implied by a vanishing theorem of Ambro and Fugino. And it turns out that this vanishing theorem of Ambro and Fugino also fails in general in positive characteristic. Okay, so this, so I should also say, yes, so not only in this computation do you use this vanishing theorem, but it is also what goes into the proof of this over the complex numbers. So here, proof uses a vanishing theorem of Ambro and Fugino. So let me call it Ambro-Fugino vanishing. Okay. So let's discuss what happens in positive characteristic. Sorry? Yeah, so it implies that the local ring at that point is S3. Yeah, yeah. Yeah, yeah, yeah. At that point. Okay, so in positive characteristic, this vanishing theorem can fail, and the reason is the following. So in characteristic greater than 0, there are wild elliptic surfaces. So these are just an elliptic surface that has the property that, for example, if this is over a smooth curve, that you have some torsion in the higher direct image. But let me write like this with this property. Okay. So examples of this has also been known for a very long time, and this actually tells us that this theorem fails in general in positive characteristic. Because if we consider the relative cone with respect to such a wide elliptic surface vibration, then for such a point, that point is the point that is not a log canonical center, but we are not S3 because this is the same as the H2 we are interested in. Okay, so this implies this Ambro and Fugino vanishing fails, and it also implies that theorem star fails. And this is in all positive characteristic and dimension very negative. Okay. So I now want to discuss the importance of this theorem over the complex numbers in the modular theory of varieties of general type. And I also want to discuss what we know about the consequences of this failure. This is the second part. Okay, so we are going to start with a little survey about the story over the complex numbers. Okay, so following Collar and Shepard-Barron, such a modular theory of varieties of general type should really be first a modular theory up to birational equivalence, and so we should consider canonical models. Okay. So we consider some flat family here over some smooth curve, and the fibers are canonical models. However, if we now want to have a good proper modular theory, then this means that possibly after some extension of the base, we want to extend this family to a family over a projected curve, where the fibers are still belonging to the family with a hat. And so the approach is, following Collar and Shepard-Barron, we consider so-called stable families. And this is some pair X delta, where we have two conditions, and we need to impose both a global condition and a local condition for having a good theory. And so the local condition is that these fibers should not be too singular, so they should have low canonical singularities, or actually slightly more general, they should have semi-low canonical singularities. So this semi here, it is a relaxation of normality. We still have to be S2. This is very important for us, but we relax the R1 assumption. And secondly, one should impose some global condition on this family. And the condition to impose is that this canonical divisor, first it should be R Cartier or Q Cartier or something like this, and then it should also be ample. Okay, so these are the stable families that they consider. So now let me just sort of briefly outline what goes into showing that there is a compactification now, because this is where this theorem star will play a role. So now the question is how to compactify. Okay, so this is usually done in two steps, where each of the steps takes care of sort of the local or the global conditions separately. So the first step is maybe usually called semi-stable reduction. And it is some form of the following. So possibly after some base change, sorry, this should maybe. I give it here, so show that this is it's an open of a curve. So probably after some, possibly after some base extension, we can find actually a log resolution of this family, where these fibers are simple normal crossing, and this log resolution actually do extend. So in the first step, we are finding this family here that has a reduced simple normal crossing fibers. But we took a log resolution here, so it's not necessarily an extension of our original family, right? Okay, so the second step uses the minimal model program, and we take the relative canonical model of this pair over this curve. And so this takes care of the second condition by a sort of definition of relative canonical models. So in the second step, okay, so now XC del C definitely satisfy the second condition, but we have to check that we didn't introduce worse singularities on the special fiber here in this process. Okay, so what we need here for this to be a stable family is that the fibers are still similar canonical. And so the subtle thing here is to show that these fibers are S2. So we need that the fibers over any B in this curve are S2. So this is quite subtle, but it is directly implied by theorem star. So maybe I should also say, because these are relative canonical models, it's also an extension of our original family, because the uniqueness properties of relative canonical models. So really, to conclude here, we really need that this is S2, and this is exactly what we need. Okay, so now in positive characteristic, we don't have theorem star. So suppose that we could carry out all of these previous steps, and we have ended up with this canonical model here. Is this going to be a family, a stable family? So we just know that we can not conclude that these fibers are S2 because we don't know theorem star, but we actually know something more. So there is a recent result of Collar that treats this question. Okay, so this is due to Collar last year. And it actually shows that in all positive characteristic and all dimensions greater than or equal to 3, there exists flat family x comma delta over a curve B such that so the fibers they are even better than low canonical. So but let me write LC, and the canonical divisor here is semi-ample and big over B. And so if we take the canonical models, it's just defined by the semi-ample and big divisor over B, then so these are log canonical of dimension n. So this was what my n means here. Okay. So in all positive characteristic and all dimension greater than n, there are families like this where the fibers are n-dimensional, have the right singularities, and we have this condition, and such that these fibers is not S2 for some B in B. Okay. And it also shows that all of these conditions here, they remain after any possible base change. And so if you look at some affine open here, where this is a stable family, then if you run this approach, then the stable limit that you would get is precisely this canonical model. So it exists and everything in this example, right? But the fibers are not S2, so this is not a stable family. Only stable after taking normalization. Okay, so this basically shows that this, at least without reformulating this theory, this doesn't work in positive characteristic for stable families of n-folds, for stable 3-folds and higher. Okay. So the natural question now that is not covered is, what about stable surfaces? Yes, so definitely one needs to reformulate what one means by stable families to sort of incorporate this kind of behavior, and it's not completely clear how to reformulate that, I think, for the moment. So the question, maybe put it here. Is now, what about stable surfaces? Okay, so these examples were not, stable surfaces were not covered by these examples. And if we are interested in families of stable surfaces, then our total space is of dimension 3. And so this is why we now are going to discuss this in dimension 3. So X is of dimension 3. Say over an algebraically closed field. And for the results, we are actually going to have characteristic greater than 5. I put it here in case I forget to mention it somewhere, but I will go back to this. Okay, so what happens in dimension 3? So a lot of things happen. So the first thing is that if X is a threefold, then actually KLT implies Macaulay as long as you avoid characteristic 2, 3, and 5. So if P is not equal to 2, 3, and 5, then actually KLT does imply Macaulay. So this result is due to, so it's proved in sort of 2 steps, and one step is due to Hakon and Wittecek, and the other one due to myself, Berlusconi, and Lassini. And so this says that this pathological behavior of KLT singularities, positive characteristic, is actually restricted to low characteristic, only characteristic 2, 3, and 5. And in higher dimensions, we actually don't have any examples of KLT, but not Cohen-Macaulay singularities of arbitrary large characteristic in a fixed dimension. So it could be that this is restricted to low characteristic. So let me point out that these properties of low canonical singularities that we are discussing do not have this behavior. Okay, so this theorem star fails in all positive characteristics in dimension 3 and higher. Okay. So we cannot hope to sort of save the day for stable surfaces by saying, okay, this theorem is at least true in low characteristic. So that is not at all how this goes. Instead, we have the following theorem, which is really squeezed in. So this theorem is not true in higher dimensions. So this is the main theorem today. And this is with Berlusconi and Patek Philippe this year. Okay, and it says that if X is of dimension 3, and the characteristic is not 2, 3, and 5, and we are definitely over a perfect field, and we have a pair X comma H that is semi-log canonical, and H is a reduced Cartier divisor. Okay, so this is the important assumption here. Then for all closed points contained in this Cartier divisor, actually theorem star is gonna hold for those points. Sorry, so now we are just, it's equal to 3, sorry. Okay. So first, let's just note what this implies. So a direct implication of this is, of course, that this Cartier divisor is S2 because the underlying variety is S3 at all of its points. And moreover, in the setup where we were talking about this moduli setup, right, when we are looking at these canonical models together with a fiber, then this condition is satisfied, and these fibers are reduced Cartier divisors. And so this theorem applies to this setup for stable surfaces. And so this implies that these fibers are S2 in KSB setup for stable surfaces. Okay. So in general, this is not true at points that are not log canonical centers. And I mean, I should also maybe note that any point inside H is, of course, not a log canonical center of X. Okay. So, but this is really an extra assumption that we have to impose here so that we can say something about being S3 at that point. Okay, so for the last 15 minutes, let me say something about the proof of this. Sorry? I don't know if I formulated this badly, but this point could definitely be contained in the log canonical center of dimension 1. Yeah, so that log canonical center will not be contained in H, but yeah, I think when I discuss the proof, maybe, yeah. Okay, so sketch of proof. So the idea is really to understand geometrically the failure of theorem star. And so the way to do this, so we are looking here at a closed point that is itself not a local center. And so if this point is not contained in any local center, then as Kauscher said here, we are KLT around that point, and so we are S-free if we avoid KLTs 2, 3, and 5, just by this 3.1 here. And so we can assume that this point is contained in some minimal local center, and because we are in dimension 3, we can assume that this minimal local center is of dimension 1. So X in C, minimal LC center. Sorry? I don't have any base, sorry. No, now I'm just talking, yes. So an implication of this is the following statement, but now I'm just discussing the proof of this theorem. So X comma H is. Okay, so now I'm just, basically what I'm doing here, I'm just saying X is a low-canonical freefold. Let's try to understand when is the depth as a closed point gonna be free. Okay, so that's what I'm doing here. Okay, so the way that we will study this is that we are gonna extract low-canonical places that are living over this low-canonical center, and the way to do this is to consider a DLT blow-up, which means that all of these exceptional divisors, they are low-canonical places living over C, and we are extracting enough of them such that this underlying freefold here actually has KLT singularities. So here Y is KLT, which if we use now, if that we avoid characters 2, 3, and 5, implies that we are S-free at all the points here. Okay. So now the main technical input is the following. So we are interested in this, this was X. We are interested in this local cohomology. And sort of the main theorem here is that we can construct such a DLT modification with the property that what we saw is true for these relative cones actually holds true also here. So that this group is controlled by the section supported at the point X of the induced vibration. So here, this is E. So E is some surface that is general, not irreducible. The union of these exceptional devices. Okay. So I'm not going to comment on this, but this is the sort of main technical tool here. And now let me continue. So now if you have this, then you can very well understand geometrically when this is not S-free, because it means that this group is non-zero, and this you understand. Okay, so if this is not zero, then we have a surface, not particular, maybe not irreducible, but it's fibered over some curve, and these situations have been studied. And they cannot happen in positive characteristic. And if we do have a torsion here, then all of the fibers over this point X they have to be multiple. So every reducible component has to be multiple of multiplicity divisible by p. So this implies that this fiber is multiple. And this is the way to conclude, because if you then have a pair of x comma h, where h is a Cartier divisor going from x, then pulling this back and restricting it to the exceptional divisor will give you a log canonical pair. But that the fiber appears with its multiplicity in that formula. And so this cannot happen in that case. Okay, so this can not happen if x in H. So the Cartier is, of course, extremely important in concluding. And of course, also that this has controlled singularities. Okay, so I wanted to end my talk today by sort of summing up where we are with respect to these questions, and also I wanted to state some open questions on this topic. Okay, so the first sort of question is, of course, can we now conclude the properness of the moduli stack of stable surfaces of volume V over an algebraically closed field? So properness in characteristics p greater than 5. Okay, so basically what we have seen now is that this is okay if we could carry out the other steps. And so the first step was to have some form of semi-stable reduction where you extended or you constructed a family with these good reduced simple normal crossing fibers. So this step is not known in positive characteristic. And basically what we can see now is that, okay, this properness is okay up to having some form of the first step. Okay, so at least not in this generality, this is not known. Okay, so the second question that the question I wanted to end with today is more vague, and it's the following. So, how to formulate moduli of stable n-folds in positive characteristic for n greater than equal to 3. So this is, I mean, this seems to like, here the formulation of the problem can go us over the complex numbers, and here it seems we have to reformulate. No. Yeah, so I guess there is some versions of this known, but no, so now I'm talking about this whole setup of the stable families. So the semi-log canonical singularities and so I guess There is a paper of like Scholt-Fatek-Falvi that discusses sort of this question and sort of reduces it to these two steps. And I guess maybe that's where this comes in. I'm not sure.